Hello, let's start this lecture for the course Numerical Methods in Engineering. This is lecture number 1, and it's chapter 3. And this chapter is based on this book, Numerical Methods for Engineers by Stephen Chapra and Raymond Canali. So the title of this chapter is Approximations and Round-off Errors. So it is important to consider approximations and round-off errors in numerical methods. It is because for many engineering problems, we cannot obtain analytical solutions. So for those situations, we will only have to perform the numerical solutions. So numerical methods yield approximate results. So the problem with the numerical methods is that they yield the approximate results, and those results that are close to the exact analytical solutions. So we cannot exactly compute the errors associated with the numerical methods. It means that when we get the approximate results, which means they have the errors. So therefore, we need to consider approximations and errors. We need to understand them better. So only rarely given data are exact since they originate from measurements. So the data which originate from measurements is basically the exact data. Therefore, there is probably error in the input information. So in most of the time, there will be an error in the information because the data will be the approximate data in most of the time, not the exact data. Algorithms itself usually introduces errors as well. So the algorithms in mostly are those methods or procedures which try to represent the process for which we are doing the modeling in the numerical methods. So those methods are also not exact. They try to simulate or they try to represent, but they are not exactly those representations. So therefore, algorithms also will have the errors. So in those situations, we will call them as the unavoidable round-off errors. The output information will then contain error from both of these sources. That means from the input as well as the error in the algorithm. So the error is in the input and error is also in the processing. So therefore, the output will also include the errors. How confident we are in our approximate result. So this is actually becomes the main target of this type of studies. That means we want to we know that the data we get is approximate, but in that situation, our best course of action will be that to become confident in that approximate data. If you know that the data is approximate, then we must be sure that how much percentage, whether it is close to the reality, how much close to the reality that data is. So confidence we need to determine. Therefore, the more proper question becomes how much error is present in our calculation, and is that error tolerable, or when the error is tolerable, then the error will be in some certain within some certain limits. So this is the main question in numerical methods about the quality, correctness of the data. Okay, next look at a few of the terms. First of such term is the accuracy. So accuracy tells us that how close is a computed or measured value to the true value. So the definition is quite straightforward. So we know that the true value of certain measurement is, and we also measure some value. So whatever is the difference between the measured value and the true value, that will show the accuracy. So if the measured value is the same as the true value, so then it is 100% accurate. Otherwise, there will be some difference, and then difference will cause the inaccuracy. The next definition is the precision. So often we confuse these terms, accuracy and precision, but accuracy is different from the precision. Precision actually represents the reproducibility. That means how confident or we are to produce the same result. Okay, that means it is like maintaining the quality of the product. Okay, so with let's see. So definition is how close is a computed or measured value to previously computed or measured value. So if you measure the value one time and then measure the value another time, so what is the difference between them? If the first time the value was very much different from the second time, then we'll say that these measurements are not precise. But every time maybe we take the measurements like 3 or 4 or 5 times, and each time the measurements are quite close to each other, we will say these measurements are precise measurements. But having a precise measurement does not necessarily mean that the measurements are accurate. So we can see that a measurement can be accurate but not precise, or on the other hand, a measure may not be accurate but the measurement can be precise. So later on in the next slide we will see such scenarios. So on the other hand, if we have the accuracy, then we can also define the inaccuracy. So it is the systematic deviation from the actual value. So it is also sometimes called as the bias. Okay, so the difference between the measured and the actual value. And if it is a systematic, that means always on always positive or always negative. So then it is a kind of like systematic deviation. And then on the other hand, imprecision or imprecision tells us about the uncertainty. So it is the magnitude of the scatter. Okay, so how much the values, different measurements are different from each other. So if they are very much different with each other, that means our measurements, the quality of our measurement is pointing towards the uncertainty. Okay, so this is the chart to show some of the relationships between the accuracy and the precision. So for example, if we have these 4 figures A, B, C, D. In figure A, we can see that the data is scattered along various places. So we can see that the data is not accurate because accurate data will be then when most of the points will be in the center. Okay, here we are assuming that the accurate points will be the one here where the most of the points will be in the center, but we can see that the most of the points are not in the center, so data is inaccurate. And we can also see that the different points are also away from each other. Okay, some point is here, some point is here, so the data, so it is also imprecise, so inaccurate and imprecise. And over here we can see that the points are scattered along. However, the points are almost evenly distributed about this central point. So here in this case, this is the result of the accurate but imprecise. Over here we can see that this is the example of the inaccurate but precise, so that the points are much closer with each other. Okay, and here we can see that the all the points are near the accurate area, and but they are also closer to each other, so the points are accurate and precise. Okay, so this is A is inaccurate, imprecise, B is accurate but imprecise, C is inaccurate but precise, and then D is accurate and precise. Okay, so this is the definition. this is the depiction of the accuracy and the precision. So let's talk about the significant figure. So significant figure is a way to represent the numerical data, and it helps us to understand the quality of the numbers. So number of significant figures describe number of significant figures indicate the precision. Okay, that means the significant digits of a number are those that can be used with confidence. So for example, the number of certain digits plus the estimated digits. So when we want to find the significant digits, so we have to calculate the number of certain digits plus the one estimated digit. Okay, so to illustrate it, so look at this number 53,800. So how many significant figures are here? So here we cannot say for sure that how many significant figures are here, because we don't know that these leading trailing zeros are very much precise or not. So whether we have used this number as an approximation. So for example, we may see that maybe the exact figure is 53,810, but maybe we have rounded off to exactly 800. So in this case, we may see that the significant figures are 538 and then one estimated digit. So there may be 4 significant digits, but here we must be sure that how much accurate our measurement is. So to better represent the significant figures, the scientific notation is used. So in this case, when we talk about the scientific notation, so for example, when we have a number and then that number is followed by the decimal place, and then the numbers after the decimal places times 10 to the power certain number. So in this case, when we write it in the scientific notations, so then we can say that there are certain number of significant figures. So here we have these significant figures are 1, 2, 3. So 5, 3 and 8 are the significant figures, and after that 5, 3, 8 there will be 0, so that will be insignificant. On the other hand, if we write 5.380, and we can see that in this 5.380 there is a leading 0 over here. So but that leading 0 has been placed over here for a purpose. So in this case, the significant big figures will be 4, and similarly if there are 2 zeros, then the significant figures will be 5. The case on the other hand is a little bit different. So zeros are sometimes used to locate the decimal point, not the significant figures. So in the case of when after the number is less than 1, and then there are zeros after the decimal place, so that zeros are not counted towards the significant figures. So therefore 1753 will have a significant figures of 4 only. And similarly in this case, whether there are 3 zeros, 4 zeros or many zeros, those significant figures will not be counted. Any number after that as 1743 will be any number after those zeros will be counted as the significant figure. So in this case, if for example, if we put for example a 0 over here, it will, instead of 1753, it is 1703, so then still it will have 4 significant digits. So in all of these 3 cases, there are 4 significant zeros. So these zeros are not counted in the calculation of the significant figures. So let's talk about some of the definitions of the error. These are called as the error definitions. So the first formula for the error definition is the true value is equal to the approximate value plus the error. So conceptually it is correct. So if we have the approximate value and then we know the error, then we add them together, then we will get the true value. And then in a symbolic form, it can be, you can represent like this. So ET is the true error. Okay, ET is the true error. So if error and then we take approximate on the other side. So therefore from this first equation we can find that the error is equal to true value minus the approximation. And in fractional terms, so the it will be the fractional error, true fractional error, relative error will be called as the true error divided by the true value. So if we have this true error, we divide it by the true value, and then we will get the true fractional relative error. In percentage terms, true percentage relative error, which will be represented by epsilon t, is equal to the true error divided by the true value multiplied by the 100. So the answer will be given in the 100%. Okay, so for numerical methods, the true value will be known only when we deal with functions that can be solved analytically, and which are normally the simple systems. So in real world applications, we usually not know the answers a priori. That means beforehand, or we don't know such answers in most of the times. So therefore, the previous equation, where we are using the true error and the true value, has limited application. So most of the time we don't know the true value. So in those situations we use a modified form of the equation. In that case, we say that we have the approximate relative percentage error epsilon a is equal to the approximate error divided by the approximation times 100%, because we will get the answers in terms of the approximations. And then from the first approximation and then the second approximation, we get the difference between the two approximations that will give us the approximate error. So using the iterative approach, and we can then find the approximate percentage error. So that means approximate error, it will be the current approximation minus the previous approximation, okay, and then divide by the current approximation. So, and we can find then epsilon a, which is the approximate percentage relative error, and this relative error can be plus or minus, okay. So depending on how the approximations are going, whether the approximations are increasing, iterative approximations are increasing or decreasing. So however, for comparison purposes, that means where we want to stop, so we use the absolute values for the approximate errors. So the computations are repeated until a stopping criteria is satisfied. And what is that stopping criteria? The stopping criteria is then compares the absolute value of the approximate error, percentage error, with the some pre-specified percentage tolerance based on the knowledge of your solution, so which is represented by epsilon s. So it is a pre-specified percentage tolerance value. So if the absolute approximation, if the epsilon a absolute value of the epsilon a is less than epsilon s, then I think then we can stop the iterative process. So if the following criteria is met, so in this case, then how we can calculate the epsilon s? So it has been determined by some derivations that epsilon s is equal to 0.5 times 10 to the power 2 minus n, and that is the answer is in the percentage terms. So where n is the number of significant digits. So for example, if we want the answer in n significant figures, okay, so by using this relationship, we can find the value of the epsilon s, which is the value in the percentage relative terms. So so once we know the epsilon s from here, then we can compare it with the absolute value of the epsilon a, and then the iterative criteria can be met with that process. Okay, so let's talk about the round of errors. So previously we talked about the approximations, and now we talk about the round of errors. So what are the round of errors? So to understand the round of errors, so we can understand these numbers such as pi, e, or square root of 7. And from our knowledge of mathematics, from our knowledge of these numbers, we know that these numbers cannot be expressed by a fixed number of significant figures. Because these numbers have the infinite number of digits after the decimal place. Computers use a base 2 representation. They cannot precisely represent the certain exact base 10 numbers. So this is also one of the reason for the round of errors. So we all know from our basic knowledge of the computer systems, the computers, the basic numbers or the basic mathematics involved in computers are the two situations, on and off situations, and these on and off situations represent the 0 and 1 number. So that is called as the binary system. So since computer represents the binary system, and then in our common arithmetic we use the base 10 numbers. So for each corresponding base 10 number, we don't have the representation in base 2 numbers. So which means that even if there is a base 10 number in exact form, if we want to convert it into the base 2 form, we may not find the exact representation. So in those situations, of course, then there will be the approximations. So the numbering system, the difference in the numbering systems between the computers, base numbers, and the normal base 10 numbers numbering system also introduces the round of errors. We will see this with the help of some examples also later on. The fractional quantities are typically represented in a computer using the floating point form. So another reason for the round of error is the floating point form representation in the computer systems. And how the floating point form is represented. So the floating point form is represented in this form. Okay, so where, for example, wherever there is a number, for example 237, so that 237 will not be represented like 237 in the computer. It will be represented like 2 into the multiplied by some base times the power. Okay, so where m will be called as the mantissa. Okay, and that will be the fractional part. Okay, that will be the part which will include the decimal places, and the integer part of that number will be the this number which is shown in the form of the pink in pink color. So this will be a number raised to the power some other exponent. So there will be the base of the number system, and then it will be the exponent. So if the base of the number system is 2, so there will be that will be the binary system. If the base of the number system is 10, then that will be the decimal system. Okay, so so here in this figure it is shown that there is some relationship between the binary system and the decimal system. So first of all, in part A, we can see that this 86409 is a decimal system number, and this decimal system number is represented like this. So it is 9 times the 10 to the power 0. Okay, and then if we move to the towards left, so it will be 0 times 10 to the power 1, and 4 times 10 to the power 2, 3, 6 times 10 to the power 3. So as we move along this number from right to left, we increase the powers of 10. Okay, and the 10 is basically the base of the decimal system, and in this way when we add up these quantities, then we get this number 86,409. So similarly, on the other hand, in the binary system, the numbers only include 1 0 1 0 because there are only 2 digits in the binary system, 1 and 0. So the any binary number in the computer system will be represented in ones and zeros. So if one of that binary number is 1 0 1 0 1 1 0 1, and if we want then that binary number by the same analogy will pan out like this. So it will be 1. So this 1 which is on the right hand side will be basically 1 times 2 to the power 0, and then if we move towards left, then it will be 0 to the 0 into 2 to the power 1, and then it will be 1 to the 2 to the power 2. So as we move along from right to left, we will use the base 2, and then we increase the powers of 2 from 0 to the last digit. Okay, so in this way, when we represent it like this, and then it is a kind of a conversion from a base 10 base 2 to base 10. So it will represent, when we add up all these numbers in base 10, so we will end up as 173. So this binary number in base 10, that means so this number in base 2 is represented to this number in base 10, 173. Okay, so with this small introduction about the binary and the decimal numbers, so here we can see that how the numbers are represented in the computer system. So this is the representation for an integer. Okay, integer. So as we can see that the computer stores the number in the form of the bits. So this is a let me count 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So this is a 16-bit computer. So for example, if the computer is a 16-bit computer, that means that computer stores each word in 16 bits. So that computer will then store that number in the form like this, whereas the first bit will represent the sign of the number. So if the first bit stores as 1, then the sign will be minus. If the first bit stores as 0, then the sign will be plus. Okay, and then the remaining numbers will be used for storing the number. So in this case, that number is 0000, and then actually the number starts from 101011001. So its representation we have seen over here, 1010101. Yeah, it's the same as this number. So earlier we found out that this was representing 173. So which will show you that a decimal number 173 will be stored as like this number in this system. Okay, in the binary format. Okay, so this was figure number 3.6, which shows the representation of the integers in the computer system. The representation of floating point numbers, that means the numbers with the decimal places, are also stored in a similar way. So in this case, the first part of that system shows the sign. The second part will show the signed exponent, that means 10 to the power 2 or 2 to the power 3, and the last part will show as the mantissa. And just recall that mantissa was here, okay, the number which is being multiplied, and then that was the integer part, the base and the exponent. So this is the representation of the floating point number in the computer system. So first is the sign, then the signed exponent, and then the mantissa. So now let's look at how the number 156.78 is represented in the normalized form. So the normalized form starts from 0 point and then the numbers. So in this 156.78 will be in the normalized form, it will be 0.15678 into 10 to the power 3 in a floating point base 10 system. So on the other hand, if there is a number 1 by 34, which is represented by 0.0241175, and then of course there are unlimited number of numbers after the digits after the decimal place. If, for example, if we have a system which stores only 4 decimal places, so then it can be represented by 0.0294, and then other places are not stored, and then in that case we can multiply it by 10 to the power 0. However, in this case we are losing one significant digit because of this 0. So if we convert this into the normalized form, when after 0 point we are starting with the non-zero number, so then we can write it like this. So in the normalized form, we will remove the leading zeros, multiply the mantissa by 10, and lower the exponent by 1. So in this case, then that number will be 0.2941. So number decimal will move from left to right, and then mantissa, the exponent of 10 will be reduced by 1, so it will be 10 to the power minus 1. So and then it will result into the extra digit which was earlier removed. So we'll get that extra digit 1. So in this case we can represent it in the normalized form. So such a normalized form follow this rule. So 1 over b less than or equal to m, that is 1. So that means the mantissa, the absolute value of the mantissa, that means in this case 0.294 will be between 1 and 1 over b, where b is the base. So base is 10, so 1 over b is 1 over b 1 over 10, so 1 over 10 is 0.1. So in this case this mantissa will be always greater than 0.1 in the normalized form. Okay, and on the other hand, if it is for base 2, it will be always greater than 0.5 and less than 1. So this is which I just said before. So therefore, for a base 10 system, it will be from 0.1 to 1, and then for a base 2 system, it will be from 0.5 to 1. So floating point representation allows both fractions and very large numbers to be expressed on the computer. However, floating point numbers take up more room. They take longer to process than integer numbers, and round-off errors are introduced because mantissa holds only a finite number of significant figures. So for this, I would advise you to see the examples in the book, and then these examples, for example, example 3.5 and the text after that is for illustration of this point. Lastly, there is a process which is called as the chopping. So what the chopping means, as the name suggests, that the chopping means removal of the extra number of digits. So if, for example, if we have pi up to these many number of digits, if we want to store it on a base 10 system carrying 7 significant digits, so then it will be 3.14159. Okay, will be 3.1492 for 7 significant digits. So 1, 2, 3, 4, 5, 6, and then 7. Okay. So in this case, the chopping error will be this much, 0.000 and then 65. So that chopping error is calculated by removing, subtracting this original number from this number. If on the other hand, if we use the rounding, so by rounding, this number will be 3.141593, because if after 2 the this number is 6, which is greater than or equal to 5, so then it will be rounded up. Okay, so in this case it will be 0.093, and then in this case the difference between these two values is something like 0.00035. So in the case of rounding, you can see that the true error is less than in the case of the chopping. However, why do we need chopping? Because some machines use chopping because rounding errors to the computational or rounding adds to the computational overhead. That means we need more computations. So since the number of significant figures is large enough, resulting chopping error is negligible, especially in this case. So chopping is sometimes useful because it involves less power of the computer to perform the calculations. Okay, so with this, the theoretical part of this topic is completed. Now let me show you some of the examples. So convert the following base 2 numbers to base 10. This is problem number 1. So I have these two base 2 numbers. If we want to convert into their base 10, so let's take this first number. So it will be 1011101. So if we take this number, then this is how it is converted into the base 10. So as you can see that the process is quite simple. You can readily see that we are continuously multiplying by the powers of 2. So we start from the power of 2 from 0. That means we start from the power 0 of 2 to the power 0, and then we multiply it by the rightmost term. Also, therefore, if we want to convert it into base 10, so we will start from 0, 1, 2, 3, 4, and 5. So this first number will be multiplied by the 2 to the power 5, and then we will reduce to 2 to the power 4, and then that 2 to the power 4 will be multiplied by the second digit, and then 1 will be multiplied by the 2 to the power 3. So we are reducing the powers from 5, 4, 3 to up to 0. So we will start from 0 from here, the power of 0 from here. And then we will do the arithmetic, and then we will add these numbers, then it will be 45. So 45 represents this number in the binary system. So this number, as an example, 101.011. So this is a binary number, but in the form of the decimal places. So for the decimal places, what we have to do is for this 101, the power of 2 will be 0. So towards right, the power will decrease. Okay, because we see that the powers are decreasing. So therefore the power of 2 will be -1. For this number 1, the power of 2 will be -2, and for this the power of 2 will be -3. So in this way, then you can see that how the arithmetic is performed. So starting from 0, if you go towards left, so 0, 1, 2, and then it will be -1, -2, -3. So here we have the powers, and then we are multiplying with the respective digits, and then we will perform this calculation. So 4 plus 1 plus 0.25 plus 0.125, it will be 5.375. So a 5.375 number in a decimal system is equal to 101.011. So similarly, we can perform the calculations for other cases as well. So That was problem number 1. And then problem number 2. Evaluate e to the power minus 5 using 2 approaches. Okay, so we know that e to the power x is represented by these formulas. So e to the power minus x is equal to 1 minus x plus x squared over 2 minus x cubed over 3 factorial. So these are the series approximations of the e to the power minus x. And this e to the power minus x can also be represented like this. E to the power minus x is equal to 1 over e power x and then 1 over this number in the reciprocal. So if we want to compute these two values and then compare with the true value of 6.37 into 10 to the power minus 3. Use 20 terms to evaluate each series and compute the true and approximate relative errors as terms are added. So for this purpose, since we are going to use the 20 terms, so it will involve a lot of calculations. So we can use the spreadsheet programs such as Excel for the solution. So for the first series, after 20 terms are summed, the result is here. Okay, 6.7455 and then 6.737947. And then this Excel sheet can be set up. So in this case, this first column shows the iterations. Okay, we are performing 20 iterations, and then how we are going to do it. So for example, we will start from the first iteration. So for example, the first is 1. Okay, the first value is 1, and the second value is because we are using we will be replacing x with 5. So if we will using the second term, then it will be minus 5. So second will be 1 minus 5, that will be 4. Okay, and in this case you can see that the second term is 4. The third term will be we will use 5 over here, 5 square over 2 factorial, and then for the third iteration and then fourth iteration, in the same way we keep on adding the values. So basically each term which is repeating is x to the power n over n factorial. And then because we can also see that the signs are changing from minus to plus, so minus plus to minus, so we can add a column for the signs to add up these values. So if you will try, you can then very easily set up this spreadsheet, and then we will perform these 20 iterations. Basically we are adding the first 20 terms, okay, one by one. So here we have added the first term, we are adding the 2 terms, here we have adding the 3 terms, 4, 5 and up to 20th. And here you can see that the values are like this. So 1 minus 4, 8 minus 1. So the values are kind of like oscillating. Okay, and then finally the values are converging. Okay, 6.7 after this 20th or 19th term, the values are like kind of converging, and then there is some and this is the true value. Okay, true value is the one we calculate from the built-in formula. Okay, so it will you can see that by these approximations the values are gradually closer at 20th term. And here you can see that this is the percentage relative error from the true values, and then the percentage approximate error. Okay, and then you can see that these values gradually decrease, and in the end we can see that the percentage relative error is still quite high, 0.11%. Okay, in this first formulation. Okay, whereas then we can see that now the results oscillates at first by n is equal to 20. That means for 21 terms it is starting to converge on the true value. However, the relative error is still substantial at 0.11% as I have seen here. Okay, so if carried out further to n is equal to 27, the series eventually. So the value eventually converges within 7 significant digits, but in this chart we have only shown up to 20th iteration. In contrast, the second series converges much faster. That means this series, if we will put these values in the Microsoft Excel, so this series will converge much faster. It attains 6 significant digits by n is equal to 20 with a percentage relative error of only 8.1 into 10 to the power minus 6. So percentage relative error is much lower in this case by 20th iteration. So in this case, the series converge quite quickly, and then you can see that earlier it is oscillating between higher and lower values, but then the series is converging. Okay, here 1 over this was the series, so you can see that here now the value is 6.737948 and then 6.739747. So there is very less difference. Okay, and then the percentage error is also less. So therefore you can see that just by changing the form of the formulation, we can converge some values much quicker than the others. Okay, next this was problem number 2, and so in the problem number 2 the main challenge is to develop this spreadsheet, so which I'm sure it is very easy, you can perform it. Okay, problem number 3. So evaluate the polynomial y is equal to x cube minus 5x square plus 6x is equal to 0.55 at x is equal to 1.37. So by evaluating, what we mean is that put the value of 1.37 here into this and then find the value of y. So it's a very simple task, but I think what we need to find out is that some other observations. So we can use in this case our limitation is to use 3-digit arithmetic with chopping. Okay, evaluate the percentage relative error. So we are not using more number of digits. So if by using the 3-digit arithmetic, then we will see what happens. And in part B, repeat A but express y as like this formulation. So y is, maybe we can represent like this formulation. So 0.55 is separate, so we can take x as common from here, and then we take x common from the other two terms and put it in the brackets, and then try to calculate and compare the results. So let's do the part A first. So in the part A, first of all, let's find the true value first. So true value is 1.956853 up to this many significant digits, 1 2 3 4 5 6 7 7 significant digits. Okay, this is the true value. Okay, this is just like when you will calculate using your calculators. However, now let's calculate this value by using the chopping thing. So for the chopping, I think we need to put the value of 1 by 1 into this term, x cube minus 5x square plus 6x plus 0.55, like this. So 1.37 cube is actually this value, but it will be chopped to 3 digits. So it will be 2.57133 will be just taken as 2.57. Okay. Similarly, the second term minus 5x square, and then it will be taken as minus 9.35. The third term is 6 into 1.37, that will be taken as 8.22. So we are chopping the figures to 3 significant digits and then finally add these all terms together. So we get a value of 1.99. So remember that the original value was 1.95 and then the value which we calculated was 1.99. So this represents a percentage error of 1.694%. Okay, so this means that by chopping, the chopping can introduce errors. Okay, so if we want to chop at, say, instead of 3 digits, if we want to chop at, say, 4th digit, then the percentage error will become lower. But that we will see for for some other time. You can see it by yourself. So now let's do the let's find the effect of the second formulation. So in this case, second formulation is this. If we use the same chopping by 3 digits and use this formulation, so we can put these values like this. Okay, 1.37 and then like that. And then first we will 1.37 minus 5 will be evaluated first, then it will be multiplied by 1.37. Okay, and then it will be, I think there is some, it should be plus 6 over here, and then 1.37. And similarly, by chopping process in this, we will multiply and then chop it to the 3 digits, and then plus 8, and then finally you will calculate that the value is 1.96 in this case, and then this represents an error of 0.161%. okay, 0.161%. so previously we got an error of 1.69%, but now it's 0.161%. so we can see that just by changing the formulation and using the same level of chopping, we can reduce the error. So the error can be reduced by changing the formulation, and error can also be reduced by the increasing the number of digits of the chopping, or using maybe the rounding. Okay, rounding, but of course rounding will introduce more computational errors, computational effort as well. So this was problem number 3. So hence we can see that in this the second form is superior because it tends to minimize the round of error. Okay, so these were some of the representative problem sets, problems regarding this topic. And that's all for this topic. So we'll start the next topic in the next class.